And today we have a guest, our guest lecturer is Professor Tonio Ball, aus Deutschland, from Germany, from University of Freiburg. And let me just introduce Professor Andrzej Cichowski from Skoptek. He will introduce Professor Ball, because they are friends from, so he will explain it.
Thank you. So, good afternoon, everybody. So, it's really great honor and privilege for me to introduce Professor Tonio Ball. I know him many years. We met a long time ago in Japan, when I worked in Japan in the Brain Science Institute. So, he visited Japan several times. We also co-supervised together one PhD student. And this student worked on EEG and ECG, so electroencephalography and electrocardiography. So probably it's not necessary to introduce Dr. Ball because he is well known. In fact, he is one of the pioneers to apply artificial intelligence, especially deep learning, to brain data, especially electroencephalography and electrocardiography. So he has a fantastic team of researchers in Freiburg University, and he makes a lot of work in this area, and his paper, his publication is very influential. I would like also to mention that we have also joint publication of NIPS. NIPS is a very prestigious conference, Neural Information Processing System, because Professor Ball had very unique data. He simultaneously recorded electroencephalography, so record on the scalp level, non-invasive, and semi-invasive electrocardiography. So we would like to find if it would be possible by using some sophisticated machine learning tools to predict how we look electrocardiographic data on basis of electroencephalographic data. And we took from his data and we together analyzed this data using tensor method. So we developed a method which is called higher order partial least squared. We probably will not talk today about this, but anyway, I'm very proud that we have even joint publication. So I would like also to add that Tonio is head of Translation Neurotechnology Lab. He is also a member of the executive board of Cluster of Excellence Brain Links and Brain Tools. Maybe you can give one detail what is this. And he is also member, in fact, founding member of the Brainchild Center Freiburg. So let's welcome to Professor Ball.
Yeah, thank you, and thanks for the kind introduction and the possibility to be here today and speak to you. And when preparing for this lecture today, Matvey told me that this would be a very mixed audience, like general public and students and professors, and I should make a presentation that's interesting for everybody. And so I tried my best now to combine a little bit more general topics, and of course this may be already known for many of you who work in this area, but then I'll also talk more really in depth about our research, and this is then maybe interesting for those who really work in this area. So I tried to make a mix, and by the way, when I will be talking and there are questions on the way, if there's something you would like to ask, please raise your hands, and we can also make this quite informal. So, and if there's something to discuss, don't necessarily wait until the very end, because maybe this can take a while. And therefore, please ask me. Yeah. So, as I said, thanks again for the possibility to be here today at this really amazing institute, and we already had a lot of interesting discussions over the afternoon around the general area of artificial intelligence, AI systems, and many interesting applications that one can do with such systems. And this is the topic that my group is working on and what I want to talk about today. And as a very first question, I don't know, did this work with this online questions? Okay, I think we already see some kind of trend. Yes, it's now it gets then it's a social experiment. Oh, okay, who was that? Who was? No, that's okay. But okay. So yeah, this is interesting. So here, really, the big majority says they are already using this, and then let's switch back. But it's okay if you keep answering because we will go back to this online thing later on. But definitely, the big majority thinks that you're already using AI systems in your daily life. That's interesting because actually. Because there has been a recent survey in the US, and one of the main results there was that 63% of the consumers in these countries here were already using AI tools without even realizing it. So it's interesting that this technology is maybe even already more widespread than many people think. But only I think here this audience is really different, so you're better informed and you actually realize what you're doing. But in the general public, this doesn't seem to be necessarily the case. And of course, we're using, by the way, maybe can you turn down the light in the front of it? Is this possible? So then maybe. No, but one can see it anyhow. So, okay, of course we are using this kind of tools in many areas already, like search engines, speech recognition, face recognition, and there has been really a huge increase since, I would say, approximately, let's say, 2012. And one term that you get repeatedly, you come repeatedly across in the media is the AI race, also since, let's say, around 2012. And, well, of course, you could argue with that, but many would say that now in 2019, really leading in this race is the US with tech companies Google, Amazon, and Facebook. And the Russian president has stated in a speech to students that in the future, the nation that will lead in AI will be the ruler of the world. So I think this is really a strong statement, but it's very imaginable. And China plans to actually be the ruler in the world in AI by 2030 and will to become, and this is like a governmental strategy to become an AI superpower by 2050. And they are already the nation that is spending most funding in this area, more than this crazy number of $1 billion per year, according to the Financial Times. So there's really a huge effort in many areas, and also this guy has heard about it apparently. So Donald Trump was actually thinking what he could do about the situation because he understood that this is probably important and something should be done. And so in 2018 he installed a committee to advise him on AI, and at the same time he made himself chair of this committee, while the other people who were appointed, most of them did actually not exist. So basically Donald Trump made himself his main advisor on AI. Well, okay, so I think his problem is not with artificial intelligence. So, okay, so there's this big interest in this area, and another well-known event was that underlines this, that Elon Musk, together with more than 100 technology leaders, sent a petition to the United Nations where they asked for new ethical regulations in this area, and especially AI weapons, and they stated that the introduction of AI technology would represent a third revolution in warfare after the invention of gunpowder and nuclear weapons. So they really take this very seriously, so I think it's a serious topic. But on the other hand, and this is really what I want to talk about today, is that similar to this, let's say, dark side of the topic, also many think that IA systems could be like the introduction of antibiotics and molecular medicine, be transformative for medical and healthcare applications. And so this, from my background, I'm a medical doctor, so this is really what I'm interested here in this area. And another thing that is, of course, very often mentioned if people talk about AI is that looking back into the history of machine learning and AI research, there was a first wave of interest around the 1960s, but then there was also a disappointment because the systems that were developed could not fulfill the big somehow the expectations that were generated. So there was something that is called the first AI winter. And then there was a second wave of interest around the 1980s with these, what was back then called expert systems. But again, these systems did not fulfill the high expectations that people had, and there was a second AI winter following this period. And then, of course, now, after something has happened twice, and now again there's this big interest and high expectations in this technology, many think that maybe a new winter is coming. So maybe this is again just like a big hype, and it's maybe just again a wave, and the third AI winter is maybe coming soon. And this is also something I want to talk about, why at least, of course, it's impossible to look into the future, especially in this area. Normally all predictions that you make are wrong anyhow, but at least I want to explain why I don't think that we will get real AI winter again as we had before, and but this will be at the end of the presentation. So, as I mentioned, there's a big interest in machine learning and AI in the medical field, and this is a cover from 2016 from Nature. This was about to study training a deep neural network, and we'll come to that, to automatically diagnose skin cancer from photographs. And in this study, this deep network was had just to classify the images as being suspicious of cancer versus being healthy, and was compared to the opinion of 30 certified dermatologists, so real medical experts from this area. And one interesting aspect of this situation is that in all cases these skin lesions were removed, and based on histology it was kind of known if this was really cancer or not, so there was some ground truth to compare the results against. And actually in this study, this AI system was as good as these 30 specialists. And by the way, in the meanwhile, there's a follow-up study from 2018 where a newer and improved network was even statistically significantly better than dermatologists in doing this kind of diagnosis. So this is just to give you one example of what already can be done with such systems today. But of course, diagnostics also in radiology is an obvious area where this can be useful, but there are also other areas like, for example, prediction of individual side effects of a treatment, like personalized medicine, where this can really be very, very useful, and or surgery robotics, controlling robots for complicated surgery. And again, in this area, there are huge investments that are currently undertaken, and all these big companies that I mentioned earlier are really interested in investing also in this medical field. So, but now before getting into more details, some more general remarks about what we're talking about here. And as I said, for from computer science, this is of course nothing new, and I don't want to go into a lot of detail. So, especially because AI is really hard to define, so let's rather look at what we are now really talking about, and this is this subfield within AI which is concerned with machine learning. So this is definitely not all of AI research, but it's a very important area. So then what is traditional machine learning? Now this is also interesting because later on I'll talk about the differences now with the new methods like deep neural networks. What's the difference between traditional machine learning and these new methods? And so very simply, if, let's say in 2010, if you were a computer scientist and your task was to classify images, let's say like in this example, you have many images with animals or something else, and your task is to automatically classify these images into, let's say, cats and dogs and so forth. So what would you have done back in 2010? So the way these problems were approached was that you, as a human expert, would have somehow sat down and thought about the problem. So how can I decide whether an image is a cat, a dog, and so forth? And people came up with many smart ways to define features based on these images that then could be used to make these decisions. So this was, in a way, the main, let's say, intelligence in the process would have been you as a human expert thinking about the problem and then coming up with, now without going into any detail, with some kind of features derived from the raw images, which can be then quantified into some numbers and fed to a classifier to get the decision. So that means back then machine learning was largely done on features defined by human experts. And these experts, of course, were specific to the domain. Someone who would have been an expert for images was not necessarily also an expert, let's say, for analyzing speech data. And so this was the state of the art, let's say, in 2010. And but then, since then, a method that I'm sure all of you have already heard a lot about has become very important in this field, and this is a subfield of machine learning called deep learning. And this has mainly been driving this AI move since 2012. And these methods are based on artificial neural networks, and I'll come to that later on. And it's mainly called deep learning because these networks have many layers and are able to learn a hierarchy of representations. But you will see more of that. So now, just again for those who haven't seen this before, just like a very schematic picture of such a deep network. So here these dots would be the neurons, which are very abstract neurons, one has to say. Basically, it's just like a summation of inputs combined with a simple nonlinearity. So this is very different from the neurons, of course, that we have in our brain. So one main difference in the typical implementations of deep networks is that the networks in our brain have as their output action potentials. So it's kind of an all or nothing response, while these neurons will give you really a continuous number as an output, and this is of course a very fundamental difference. And then, but another really now very important difference to the methods that I have described before is that with this kind of method, deep learning with artificial networks, what you would feed into your network is now not some features that you have somehow thought about, but typically what you feed into these networks is really the more or less raw data. So for example, with images, you would really feed an array of color values as the basis of the decision into this network. And this is really a very, very important difference to traditional methods where you as a human were still the one who had to think about the features. This is now not necessary anymore, but some of the feature representation is internally learned by the networks when they are trained. And so I will not talk about the whole training aspect and so forth right now. So there are very good textbooks and online resources if you're interested into that. But basically you would train the network on many, many examples so to adjust the weights between the neurons to make it perform the task that you wanted to perform, like here, giving you the right output, cat, dog, and so forth. And once you have trained your network, you can then deploy it to new data that it has not seen before, and in the best case, you will get the right answer. So, but remember, basic, very important difference to other methods is the input is the raw data. So this is also called end-to-end learning, and the idea is that this is representation learning on the raw data. And this whole concept is actually, at least in parts, inspired by how we think our brain works, and is actually using a few concepts from the early cortical areas in our brain. But as I already mentioned, for the difference between spiking neurons and these abstract neurons, many aspects of these networks are very unphysiological. Now, the whole history of deep learning is very tightly linked to the ImageNet challenge. So who of you has already heard about ImageNet? Can you raise your hand just to get an impression how many? Again? Okay. Yeah, so quite a few, but for those who haven't heard about it, so this was a very prominent competition in computer vision that was started in 2010. And here the task was very similar to what I already explained. This was classification of images, but in this case, this is not only to say like cat, dog, bird. So, but in this ImageNet challenge, the answers are very detailed. So there were 1,000 different image classes, and the right answer would not be just dog, but for example, I don't know what's the specific dog. Poodle. No, not even poodle, but so really very, very precise names for the different animals, and not only animals, but also exotic kinds of clothing. So this is the famous ImageNet challenge. So 1,000 object classes from over 1 million images in the database. And in 2010, when the challenge was started, the winner, and this was really a very prominent competition, so really the best groups worldwide participated regularly in this competition. So the winner had an error rate of 28%. And this was considered an excellent result, so it was the winner. It was like the world champion in image classification. And the next year, the winner had an accuracy of 26%. And it's important to keep in mind that it was different images. Each year, the set of images that had to be classified, of course, was a new one. And so it was not possible to learn from the results of the previous year. And back then, I think it's fair to say that probably no one expected that something fundamentally would change over the upcoming years. And
what is human classification here?
this is a really good question. what is the human classification error in this task? So I come back to exactly this in a second very good question. But then in 2012, something completely unexpected happened. So the winner didn't win with, let's say, 24% or something, but with an error rate of 16%, which was extraordinary. People had not expected that this was possible at all. And the method that they used was a deep neural network, in contrast to the years before, where traditional methods, as I have explained before, were used. So this was the first year when a deep network won ImageNet. And I can still remember the people from the computer science department in Freiburg when they heard about this and were really amazed and said, well, this is revolutionary. 16% in this task was thought to be impossible. But this was only the beginning. So from 2012 on, each year another deep neural network won the ImageNet competition. So the traditional methods were not competitive anymore by a large margin. And you can also see from the names here that the architectures became more and more complex. So AlexNet that won in 2012 had 8 layers, GoogleNet in 2014 already 22, then the residual network architectures were introduced with much more layers. And then it's what you just asked, what would be the human performance? And you can often read that in ImageNet, the human performance is 5% error rate. However, it's really no one really knows, because this 5% is a number that comes from a blog post of one very famous deep learning hero. And he tried it out himself, and after some training he had an error rate of 5%, but actually there's no big study to define the human rate error rate, but in fact you can often read that by 2015 these networks gained superhuman performance, but it's kind of not clear. So anyhow, these error rates down to 3 or 2% were absolutely stunning, and in 2017 it was decided that the ImageNet competition was now too easy, so it was stopped. And now the community is looking for other challenges, and this whole development was really very unexpected and nicely illustrates this one basic thing that we saw repeatedly over the last years, that really tough problems where people assumed that it will take a long while to solve them were actually solved, and solved much more quickly than what we anticipated. And here's a second example for exactly the same thing, and I think again probably many have heard about this event. And this involved a computer program called AlphaGo, developed by DeepMind. And we all, I guess, know that playing chess, the game of chess, for us humans is already lost. When playing against computers, it's already lost since a long time. So probably it's already even hard to win against your mobile phone. But the Chinese or Asian, let's say Asian game of Go was a different story. And here, because there are much more possible moves, but especially also because it's much harder to actually say whether a certain constellation of stones or tokens on the board is actually good or bad. The game of Go really requires a lot of strategic thinking. So a lot of experience, and so it was, again, going back to the year 2010, I guess most people from the field would have predicted that it will still take a very long time until a computer program has even a chance against a very good amateur Go player. But then, in 2016, AlphaGo, based on deep neural networks, won not only against any good amateur or professional, but actually against the back then world champion in Go, Lee Sedol, in a match of 5 games, and AlphaGo won 4 against 1. And this was actually extremely interesting to follow, because during this game, so I still remember, it was like very bad times for us Europeans, because the games were in Asia, but I kept watching it also during the night, and it was super interesting. And one thing was that these games, there were also always comments by Go experts which commented on the development of the games. And at one point, AlphaGo really started to make very strange moves, and the commentators said, okay, now AlphaGo has lost it, so this doesn't make any sense. And but then looking back, so AlphaGo won this game, even with these really strange moves, and AlphaGo was actually trained on historic, among other methods, on historic Go games, like 3,000 years of history of the game of Go, and came up with moves which no human ever imagined, and which spontaneously everyone said, well, this doesn't make sense, but in the end it was successful. And so this is an example where one can now really think, is this some sort of creativity? What is it? So I don't want to try to answer this question now, but at least for me, watching these games, it was a really interesting thing to see. Even the language that we are using to describe this, so the commentators somehow had no other language, I think, available than saying sentences like AlphaGo is intending to do this or that. Yeah, so this was quite amazing. And as I said, it was another example where something happened much sooner as anticipated. And this, by the way, was also the start for our interest in the area, because one of the main researchers at DeepMind, who did a lot of this work on AI gaming paradigms, was Martin Wiedmiller, and back in 2012 he was still a professor at the University of Freiburg, and he was the one who somehow told me first about deep learning. I said, hey Tonio, so there's this cool new method and it works really well, why not trying it out with brain signals? And this was actually our start, so we still published, I think, 3 papers together before he like 100% went to work for DeepMind. But actually the roots of our research are in this way somehow also linked to AlphaGo and its success. And another name, by the way, that you will always come across if you read about this whole deep learning story is this guy, Jeff Hinton. So he's one, let's say, of the fathers of deep learning. So there are many, so deep learning has many fathers, and but he's definitely one of the very well-known ones. And one reason why I like to show this image is you probably know that on Google Scholar you can look up how many citations researchers get if they have a profile there. And so Jeff Hinton in 2018 got nearly 60,000 citations. So this is really quite an enormous number. So there are not really many researchers who have substantially more citations, but this also, I think, shows you just how dynamic this whole field is, because if you calculate it, this is about 1 publication every 10 minutes, and this is already kind of showing you how difficult it is to stay on the current level of research here, and this is really extremely fast moving. So in deep learning, people will say now, maybe 2019, they will say something like, do you know this old paper from 2017 where people did this and that? It's very, very dynamic, which I also like, and but it's a challenge. Okay, so much for the more general part, but now what's our part in this? So deep learning and the brain. And as was already mentioned before, so we are working with signals that are recorded from the human brain, and so here's one example. This is intracranial EEG, and so we can, or let's say our neurosurgeons can implant electrodes in patients who need that, and we can record such patterns. So you see this is in slow motion, it's much faster, and it's just the voltage changes, so green would be negative and red would be positive, and so we can get very detailed, highly dynamic measurements of brain activity with these implanted electrodes, but I'm also very interested in non-invasive EEG because it can of course be used in much more easily and also in healthy subjects. And this kind of data is what we are analyzing, and as you can see here, this is on the one side, it has a similarity with the image data that I talked about before, because the whole thing is kind of an image, but it has also a dynamic aspect, so it's changing over time, and so we have to think how we use methods that have been developed for other applications for our data. And this is, I think, a really important questions for many practical applications right now, that we would really like to get more information out of brain signals for many practical applications, for many clinical applications. This could be very useful, and this is our main motivation why we think if we could achieve something similar, as I described before, for the case of images, also for brain signals, this would be hugely useful. And another thing that's really important if we talk about applications in the medical domain is that in many situations what we need in the end is not something like this. It would be very problematic if we have something like a mysterious machine, like a black box that we cannot understand. So especially for medical applications, we really need methods that are kind of transparent. And this is, with deep networks, kind of a problem, because if you train such a deep network, it will not automatically tell you, even if it's doing its task very good, even if it's close to perfect. It will not automatically tell you how it is actually doing this. So therefore, if you need this kind of understanding, this is a challenge, and this is also a very active research field right now, and something we have to think about. And now to show you an example what I'm actually now talking about brain-computer phases and neurotechnology. So this is a study that we did together with several partners from the computer science department and robotics department in Freiburg, and this PhD student from my group is wearing, I hope you can see that, this EEG hat, and we are recording his brain activity using this EEG setup, and he's looking at this screen, and this picture is exactly the same as he's seeing on the screen. And his task is to make this robot get a bottle of water, put water into a cup, and let him drink out of this cup. So this is his task, to do this purely based on brain activity. You see he's not moving at all, and he's trying to do this just by selecting the right actions from this menu. And to this aim, so we talked about this earlier, we implemented a 5-class classification control scheme. So basically he can go up and down in the menu, he can select and go back, or he can do nothing. And for example now, he selected approach, robot, cupboard or something, so or grasp, robot, cup, and but he could also select a different action. There's also a lot of innovation on the computer science part of it. For example, this whole menu is not static, but the system uses computer vision and laser scanners to generate, and object recognition to generate the, first of all, a representation of the environment, and then based on this representation, there's a high-level planner generating actionable plans, so things that the robot can actually do, and these plans are then presented to the subject in this kind of menu. So this, in other words, this is not pre-programmed, but this is a dynamical representation of the environment that is constantly adapted to what's happening. And now we are already at the point where the robot is now pouring the liquid into the cup. And by the way, again, this is not pre-programmed, and this was actually half a PhD in the computer science department to figure out how we can pour a liquid of unknown properties into a cup. So this apparently is not trivial, but maybe I skip a part of it. So, okay, so now we are already at the most difficult part for us. So this is where now we can see here the cup, and here it has to move a little bit, but he can in the end successfully drink from the cup. And again, this was not pre-programmed, but the robot is using online face detection to find the face of the subject, and at the final stage of the process, this is of course where it's more difficult because the cup will obscure part of the face, and in this situation, the system automatically will use the visible parts of the face to infer where the mouth actually is. Okay, so now he has managed to do this. He has.
Ich kann dir momentan leider nicht helfen, weil dein Smartphone keinen Empfang hat.
Okay. So, this is what's now not planned, but you can see that this is AI failing. So my smartphone thought I'm talking to it. So now please stay quiet. Let's see if this works. So, okay, and now you can see they're really happy, and many people were involved in this, and but our part was controlling the system based on these principles, and what I just showed to you is actually, for all that I know, worldwide, the first brain-computer interface based on deep learning. So here, to get these control signals out of the EEG, we used an adaptive version of our deep networks. So, and I'll explain now a bit more how we exactly did it. So these algorithms were not just trained before, but they kept learning during the process, and this was actually an important part of the success. So, and to give you an impression of what a brain-computer interface can be, and of course now in this example it's like a practical application that could be that one could imagine in the future would be an assistive system, for example, for severely paralyzed people. So based on this approach, of course we wouldn't do such an industrial robot, but one aim would be to translate this to clinical applications. So now a little bit more. Now what if we yes? Yeah.
Thank you. Do you understand correctly that you have two algorithms? So you analyze brain signals to initiate the movement, for example, and then you have kind of computer vision to analyze video and to control the hand.
Yes. So actually there are even more components. So there's the whole computer vision side, there's the algorithms that do the control of the robot, like really this part. Then there's the high-level planner and our part. So it's if you will, 4 different components. Yeah. By the way, the whole software that we used for this project is open source and online on GitHub. If anyone is interested, we generally try to make all our stuff available. Okay, now, yeah, so we were happy that this worked, but now where is the information actually coming from? So which aspects of brain signals are informative? And now, very roughly speaking, there are 2 basic mechanisms how informative signal responses can be generated in brain signals. And this I try to draw here, so ongoing brain activity, and if there's some kind of event, like if you, I forgot to tell this, how did he actually control this movement right, left, up and down, was by imagining movements. So he imagined moving the right hand or left hand to go right and left, feet to go down, and some cognitive tasks to go up. So this was mainly imagined movement. So if you have an event like an imagined movement, one thing that can happen is that the amplitude of some oscillatory component can be modulated, like getting bigger or smaller. So this would be one mechanism. The second would be that the phase of an oscillatory component could be systematically changed. There could be something like a phase reset at the event across channels or also across frequencies. So this would be a second basic mechanism, and of course both would also occur combined. And now, when we, and I'll come back to this, so this is important to keep in mind. So of course there are many other more complex ways how information could be represented in brain signals, but 2 basic mechanisms that are well known: amplitude modulation and phase modulation. And now when we started our work on deep learning on EEG, and now this is a little bit of an abstract scheme, but I think it's what I try to show here is that deep networks, of course, have many different aspects, many parameters. How many layers do you use? How many filters do you use? So there are many parameters and hyperparameters of such networks. So you can imagine that there's some kind of, let's say, design space of deep networks. And looking at the literature, people used many different kinds of architectures. And somehow I tried here to symbolize the size of the data set. These networks were tested on just by the size of the symbols. So mostly they would test it on 1 or maybe this should be a 2 or 3 data sets. And some of those were situations where we know that amplitude, as I explained before, was more informative, or phase was more informative. So this was somehow the picture. And from this is what it was actually impossible to say whether any of these networks would really work generally. So, or because they were all different, it was not clear, do you have to design your network according to the task, which would of course be a kind of bad if you always have to design a new network. So what you would really like is one and the same network being able to work in many situations. And this was kind of our first aim, not to generate many dots in this design space at many points, but rather to try to develop a prototypical network with state-of-the-art design features and test it on many different data sets, both such data sets where we know that amplitude is informative and on data sets where we know phase is more informative. So this was kind of our aim that we wanted to reach. And then we wanted also to find out whether, hopefully, based on this network that we wanted to find, whether we could use this as a starting point to understand what's actually happening inside the network. So how do networks trained on brain signals actually represent brain signals? So can we understand this? So this is what we wanted to do. And making like a quite long process short, the end result of our work was this architecture that we described in our paper in 2017. And here the data is somehow, this is the input side, this is the classification side, and the main design idea here is that the input layers implement a spatial filter. So here the filters at the input side kind of would look onto all channels simultaneously. So it's not a convolution in the typical sense in computer vision. It's not a small kernel moved across space, but each filter just takes all the data at once. And this allows us to learn spatial filters, which are very well known to be useful on EEG, thinking that EEG is generated by the superposition of many generators which have different spatial patterns. So this was our motivation to use these spatial filters on the input side. And then the remaining layers, so these 3 layers, we also tried architectures with more layers, but we wanted to keep it as simple as possible. So we didn't want to have any unnecessary complexity. And adding more layers did not improve the performance in this case, so we kept it at 3 layers. And these layers, actually, from this point on, the spatial aspect is compressed, and the remaining layers only look at the temporal aspect. So the network is designed to be able to extract hierarchical information in the temporal dimension. And this is hierarchy of temporal receptive fields in the second part of the network. And again, the code for this network and the tutorial and also all the data that we're using is all publicly available on GitHub. So if you're interested in that, please have a look, and if there are any questions, in this case also let us know. We are happy when this is being applied. Actually, since we published this, we are really happy that our toolbox is now used by labs all around the world, and people use this as a starting point for their own developments. And in the meanwhile, this paper has also been cited several hundred of times, so we are quite happy about this development. And but then of course, we wanted to apply this network, and first of all, we selected a situation where we very well know that it's kind of scenario A, more information in the oscillatory amplitude. And this was classification of hand movement, right, left, and feet. And in this situation, we compared the deep networks against as a baseline method. We used a filter bank transmission pattern, which works well in this situation. And here's the accuracy with the deep networks. We were statistically better by 3%. But the big difference is, and this is what I emphasized before, these deep networks are now really trained on the raw EEG data. So we just feed the EEG as it is into the networks. We don't have to think, okay, here the information is in the spectral amplitude, therefore we do some kind of, we calculate spectral power. So we don't have to do this anymore, we can really analyze the raw data. So this was the main,
Does one of those represent subjects on this work? So you have a lot of those here.
Okay, sorry. The dots are the subjects.
Yeah. So my question is, as far as I understand, one of the key limitations of EEG-based brain-computer interfaces is related to high variability of EEG signal between subjects. And even within one subject, I mean, if you collected training data 1 month ago and now build a very nice model, then you are trying to apply it today, the result can be very bad. So my question is, do you have some evidence as a result suggesting that deep learning can beat these problems? So deep learning methods can achieve good
Transfer.
robustness
Yeah, so I.
in comparison with classical method like 6P or something.
So, yeah, very good point. Just the next slide will be about transfer learning, and this is exactly where deep learning seems to be especially well working. Yeah, good point. So I can come to this in actually now. So because this is exactly another study. So all in all, I think we validated our methods on around 20 different tasks in the meanwhile. And now, as a second example, we selected a situation where from previous research we now know that it's not exactly amplitude, but now it's exactly the second scenario where the changes in the EEG phase are the primary source of information. And this is a task where you have right and left hand movement under time pressure, and sometimes you will move the wrong hand, so you will make an error. And in this situation, there's a very well-known error-related brain response, and this ERN, error-related negativity, is exactly this situation where analyzing the amplitude alone is not very informative. You have to look at the phase of the signal. And here, and now coming back to your point, we looked at transfer learning, in this case between subjects. So we would train the model on part of the group and apply it to a different person the network has not seen before. And red is our networks, and green is the baseline method, and so it was consistently better in this case. And now the important part here is our network architecture was exactly the same as before. So now we have one situation where the amplitude was informative, and we have one situation where the phase was informative, and in both these situations we could apply one and the same network on the raw data. So then next we went to a task where from a priori knowledge it was not clear at all where to look for the information, and this is now a more clinical and motivated case. Here we looked at the difference between clinical EEG recordings where the doctor said the EEG was pathological, or where the doctors said that the EEG is healthy. So binary classification, normal versus pathological EEG, and this is in clinical quite relevant problem because there's always a shortage of EEG experts, and that could be quite helpful if we would have an automatic system that could help us or help the clinicians with this task. So this is what we did next. But here, so where should we look for the information? So it's really not clear which signal component would be most informative. So just to show this, one of my students actually made a collection of all, or not even all, but of features that have been proposed to be important for EEG pathology decoding from the literature. And at the moment we have a collection of about 9,000 different features, which just shows you that doing a feature-based approach can be quite tedious. So we were very interested in, can we again just apply our networks on the raw data without having to bother about thousands of features. So to this aim we analyzed a very nice public data set published by the Temple University in the US with several of thousands of EEG recordings, and we applied exactly the same network as in the previous examples also to this task, and the state of the art before was 79% accuracy, and with our approach we got around 86, which was significantly better than the previous state of the art. So this was for us a very nice result, that with this approach we can also analyze pathological EEG recordings. And also we were very happy that actually a different group from the Netherlands, yes, and the US, they picked out, or they used our published model and said, okay, we really want to know if this is really possible, so they applied our model to a separate, completely separate collection of clinical EEG data, exactly the same question, pathological or not, and they got very similar values, and they also tried to make our network better, but the differences were not significant. So therefore, the application to clinical data now also has been validated, not only by us, but also by someone else, which is in science always, I think, important, that things also work, not only if you do it, but also if other people are doing it. So therefore, for this part, I think we can now really say that we have a prototypical EEG architecture that works in many situations. So, and this, as I said before, was for us the first step. And then, but now maybe someone can, how are we in time? I have kind of lost my sense of time, so how long have I already talked? So maybe how much time do we have left? 1 hour, okay, so and
We might be 1 hour and 5 minutes is already.
okay, so then but this is now the smaller part, just to finish this. Now we wanted to look inside these networks, and from computer vision, it's already it's known that if you look at the early layers, often they respond to simple features like edges, while in the later layers, neurons maybe are only interested in faces or something else. So very similar to what we know from the brain. But if you look in the current deep learning literature, really understanding what deep networks learn from data is a very active research area, by the way. So doing exactly the same for our networks, so just looking what's the maximally activated input for, let's say, for layer 2, we often saw neurons which were really interested in these simple oscillatory patterns, similar to sinusoidal signals, maybe not exactly, but later layers, for example, this neuron was only interested in an oscillation that would grow in amplitude, but not in an oscillation that would somehow go down or stay the same level. So this was already like the first step to see that maybe there's a similarity to these visual networks. Now, there are a lot of methods that have been developed in the computer vision or general deep learning literature to analyze deep networks, and this is also something that we now want to apply to the data. And to start, we used a very simple method to test hypotheses. So we just perturbed the input in a certain systematic way. For example, we took the amplitude or the phase of the signal, randomly perturbed these features, and so we could study what's the impact on the decisions the networks make. And applying this to the movement class data, so what we find here is that, for example, if we change the amplitude above the right motor cortex, which should be here, and make it smaller, this makes the network predict that this has been a left-hand movement. And this now, if you know how these different spectral components are organized, is exactly what you would expect from the literature. So the network has learned exactly the textbook oscillatory responses for movements. So this was for us very nice, and this was also the first time that this was shown. Then next we applied it to this pathology decoding. And here, if you look here, in the very low frequencies, 0 to 4 and to 8 Hz, increasing the spectral amplitude over the, so here's the nose, here are the ears, so increasing it, the spectral amplitude above the temporal electro positions made the network think that this was a pathological example. And again, this is exactly what you would expect from the clinical practice, because temporal slowing, so slowing of the EEG exactly in these positions, is the most well-known unspecific indicator of EEG pathology. So this is exactly what the clinicians would look at among many other factors if they would make a decision on the EEG. But in addition, so interesting for us, we also found this blue pattern here in around 40 Hz in the gamma range, and this means that this global diffuse reduction of high frequency power also made the network predict that this was a pathological example. And now this high frequency changes are something that the clinicians cannot easily look at and what they usually do not use. So therefore, this was for us the first example where by analyzing the networks, we actually got a new idea what could be informative in the signals. And this is something that we want to follow much more in the future, so maybe to discover new things that we just haven't thought about before. Now, to go even a step further, we then went to this intracranial data that I told you about before. And there, a very interesting decoding problem is if you not only look at classification of right hand versus left hand and so on, but if you really try to solve a regression task where you try to get, for example, the hand position in a continuous way, or hand velocity. And there are different movement parameters one can analyze. We have done this in a series of studies in the past, like position, velocity, speed, which is in our case just the absolute value of velocity. And interestingly, depending on which kinematic parameter you analyze, so there are more details about this in our applications if you're interested, depending on which parameter you look at, it can be either amplitude or phase or both, which are informative in one and the same data set. So this is therefore a very interesting situation for us to look at these different factors. Now this is a lot of information out here on the slide, but just one main point that you can see from this. So this is now actually really looking inside the network. So here we look at the amplitude and phase sensitivity of the units in the network in the different layers, layer 1, 2, 3, 4. And we did this analysis separately for channels that were on the motor cortex in red, where we really expect the information to be, and other channels somewhere else where we didn't expect a lot of information. And this we did for different movement parameters, velocity, speed, position, and distance, and both for amplitude and phase. And so this is now really like opening the black box and trying to see what is really happening inside these networks. And what you can see, for example, for decoding speed and the amplitude perturbation, that going deeper and deeper into the network, there's this pattern emerging that the network learns to extract spectral power changes in two different frequency bands, like low frequency power and in the beta band, which is again exactly what we expected from previous studies, where we saw that especially beta power and, by the way, also low frequency phase is highly informative about speed, but power features are not informative about velocity. And so this is exactly before it took a PhD student like 2 years to do careful analysis of the data and figuring this out. And now looking inside these networks, this is exactly what these networks kind of spontaneously learn from the data without that we have to tell them in any way that this is what they should be looking for. And this was for us really interesting to see. And now here's a different representation of the same results. Again, layer 1, 2, 3, 4. And now we encoded whether the neurons were interested in phase features or amplitude features, so amplitude neurons and phase neurons. So the vertical bars would be phase tuning, the horizontal would be the amplitude tuning like here, and the red diagonal ones would be significantly tuned to both kinds of features. Now, what we found was here that these mixed cases only occurred in layer 2 and 3, while looking at the end result, kind of, the network had learned to keep these two streams of information somehow separate. And this again was for us really interesting to see, because as you might know, this is exactly like a basic mechanism in our brains, how we process sensory information, like visual information, is that we have specialized, separate processing streams for different aspects of the input, for auditory information, visual information, and so forth. And now by looking at how a deep network represents this kind of data, it looks like that spontaneously out of the training process there are emerging like distinct pathways for different types of information that are within this, embedded in one and the same network. And this was for us an interesting thing to see. So therefore summarizing this our first step to kind of opening the black box and understanding what's happening, there seems to be a hierarchy of temporal features similar to what has been described for images, also for brain signals, and the processing of spectral and amplitude and phase appears to be organized in distinct parallel emergent pathways, reminiscent of parallel pathways in the mammalian brain. And so kind of, I think we can say we have reached our goals so far, but of course this is not the end, so there's a lot that we can do, and this very, very briefly, so I think a big step for the future will be not to look at all these different networks now here symbolically, like all these small dots, but to define search spaces for automatic architecture search. That the aim would just be to say, well, this area makes basically sense, and then use methods to automatically look for the best architecture in this area. And right now it's a really interesting time for this kind of method, because gradient-based AAS, automatic architecture search methods, are now becoming very performant, so therefore computationally efficient architecture search also becomes possible, and I think this will be really very important for the future in this area, so that you don't have to somehow manually or with simple methods try to find the architecture, but you can do this in a very efficient way. And then for us it will be also very interesting to see how the internal representation of brain signals will change if we would move, for example, from our brain code network to a more optimal architecture. How would this then be internally represented in such networks? So this is one future direction, and something else is of course that another driving force of this whole development right now is that just the sheer compute power that we have available is constantly increasing. So here's a nice plot from a blog post that has somehow collected the petaflops per second performance of the deep learning hardware that was used in different studies. Here's AlexNet, you remember, ImageNet winner 2012. Somewhere should be where's AlphaGo? It's not on here. So now this is something else. So this is AlphaZero. Okay, but this will be around here, and because this is an interesting thing that AlphaZero is like new version of AlphaGo, which was not trained on the historic games, but AlphaZero was trained by playing against itself. And then AlphaZero was put against the original AlphaGo and beat it 100-0. So therefore, this is AlphaZero. And but here the main point is that the compute power of deep learning systems over the last year has doubled every 3.5 months. So the factor from 2012 to 17 is around 300,000. And now you could somehow imagine, okay, this will probably now saturate, but I think actually the opposite will happen, because what's now a big topic in computer hardware is so-called neuromorphic computing, and this is computer chips, which, because so far from deep learning we are actually training our models on graphic cards, on GPUs, but they are of course not made for this purpose. And but many big hardware manufacturers like IBM and Intel are now very interested in developing neuromorphic chips, which are really somehow implementing neurons in the hardware. And here's the Intel version of it, which is called the E, and this has 128,000 neurons and 128 million synapses implemented in hardware. And this is a very interesting architecture, and we have actually a joint project with Intel because they are now interested in a neuromorphic version of our brain-computer interface, and this is what we are currently working on together with people from Intel. And but the big difference to everything that I showed you so far is that the neurons here on the chip are not these abstract neurons that we have used in all these studies that would give you a continuous number as an output, but this is real spiking neurons, so they make action potentials. And now Intel has invested a lot of money into these chips, but now they have a problem because they have a solution, but they are not sure what's the problem that they can solve. So which algorithms can be now efficiently be implemented on a spiking neural network? And so to solve this, they have founded what they call the Intel Neuromorphic Research Community, where they now work together with people from computation neuroscience to figure out what this chip is actually good for. And I think this is, for me, maybe the most interesting development over the last years, because if you look at the general landscape, again, maybe back in 2010, there machine learning on the one side and neuroscience on the other side was really far apart. This was like distant continents, I would say. Now if you look over the last years, these two areas are starting to merge together. For example, as I just mentioned, experts from computation neuroscience are working together with experts from machine learning to figure out what to do with these neuromorphic chips, but also many other areas between the neuroscience side and deep learning and machine learning on the other side. Concepts are somehow taken from the neuroscience and tried out in machine learning architectures, for example, for navigation, something like artificial emotions or attention mechanisms or artificial creativity. It's all active areas of research, and it's all inspired by mechanisms that come from neuroscience. And this, for me, is maybe the biggest and most fundamental revolution right now, that these two areas are really coming together. And this is also why, coming back to the initial question, if I would expect that there will be like a third AI winter anytime soon, I think this is not going to happen, because there are so many interesting concepts, and also deep and interesting concepts from neuroscience that we can now try out with advanced mathematical methods that I think that there will not be somehow a problem anytime soon that we don't know what to do anymore. So to conclude this part, I think AI systems have enormous potential, but also risks, and already today AI systems trained on brain signals, as I tried to show you, have found representations of these of our brain activity that is somehow better than everything that we thought about in the many years before, and we now try to understand how these networks actually do this. In my view, the true historic event is the convergence of AI and machine learning with neuroscience, and I think now this is more like a personal statement. I think that in the future, if we will really have advanced AI systems, we will somehow not be able, especially if you combine this with techniques like brain-computer interfaces, I think we will not be able to somehow hide our, let's say, true nature from these systems. And therefore, I think that to develop AI for economic and military supremacy is maybe digging our own grave. And I would very much hope that, and I think that through international cooperation for human AI, maybe there's really a chance of also bringing the world closer together. And the last days and the excellent conference in Samara, the visit here, for me was very much a very positive experience exactly in this direction, that excellent researchers are really interested in finding solutions for important and useful developments for humankind in this direction, and this is what I very much hope that we can do all together in the future. And with this, I want to thank you for your attention, and I hope that this was maybe somewhat interesting. Thanks a lot.
Thank you very much. Do we need to ask the second question?
Okay.
So we can go to native boards
So
for the second question from Professor
But you can also, maybe it's more interesting to ask your questions to in the remaining time.
We also have some questions from the audience there.
Because I don't, sure. If there.
Can I just put it on the mic?
Yes. Okay, so I'm very happy. So you're optimistic about the future. Me too. So cool. So, although I think some have doubts, but it's always good that some people are careful. That's good. So, but now here is the ECG, but okay, ECG would be electrocardiogram, yeah. So maybe this is not what you wanted to ask. ECG would be recording from the heart, which is. You mean EEG, yeah? Irreproducible enough. How selective is it? Well, I think just the other way around from our results and results from many groups, we see that it's at least reproducible enough to enable this kind of application as I showed you. And so enough, it would always be the question, enough for what, I guess. But I think that there's a lot of space for making methods more robust against non-stationarities. So I think that even if maybe today methods are not reproducible enough, we can work on that. So basically I would say yes. If you would have an implanted electrode at think 1 or 2, can a computer be taught to decode my thought? Yes. Short question, yeah, this works. Of course, it depends on which electrode and in which area, but basically this kind of information can be decoded. Yes, yes.
So we go for it?
Okay. Do you think that usage of human-related notions for algorithms is problematic? So who asked this question? Please stand up. Because I'm not sure if I understand it correctly, so but I think that we have no choice. So we are humans, so we will always have our human way of looking at problems, and maybe this is also good. So therefore, I think this is. I'm not worried about this part so much. I'm not sure if this is what you wanted to ask, but this would be kind of my spontaneous answer to this question. So, relating to the interpretability, human experts also sometimes use intuition. How do you think maybe there's limits for interpretability? And that's a very good question, so because intuition, what is it? So intuition is maybe, how would you define that? If you would make a decision and you cannot say really why you're doing this. So let's say for this diagnostic task, and I think this is a very good point because let's say you have an EEG, and I can very well imagine the scene that you have two experts, and this really happens not so seldom in our department, and they would disagree about whether this EEG is maybe pathological or not. So, but maybe they cannot really say why. So, of course, they would somehow have some arguments, but at some point they would maybe just say, well, this somehow looks not healthy. And then this would be exactly an intuition based on long experience and somehow implicit learning. And so I think this plays a big role in our decisions, that many of the decisions that we make are even not transparent for ourselves. We just say, well, I have a feeling this is not a good idea, and so forth. And therefore, it's a really good point. Yeah? So we are even not somehow transparent to ourselves in many situations, and this is what we then call intuition. So therefore, I think it's very likely that there could be fundamental limits to interpretability, and this will be, I think, a very interesting topic for future research. And therefore, yes, this is, I would say, exactly, maybe, and it's good to have, but it's good to have this word here, maybe there are principal limits for interpretability, which should have, by the way, very deep reasons. So there's an interesting mathematical analogy between statistical fluctuations in quantum fields and statistical fluctuations in neural networks. So just one is a complex number, the other one not, but one can use tools, and this is also what people, especially from computation neuroscience, some are really now interested in. One can use tools that have been developed in quantum field theory, especially for those who are maybe from physics. Renormalization group is one big keyword here. One can use these tools to describe the coarse graining mechanisms of networks, both simulations of real networks, but the basic ideas can also be applied to artificial neural networks. And as you know, there are also basic limits to interpretability that, if you think of quantum theory, interpretability is also, let's say, a relative term. Therefore, I think, this is a very good point, and I would say yes.
So we have 11 questions.
Also, I try to keep it shorter. Yeah, maybe, have you already tried out deep learning with primates? No. I must say I hope I'm not offending anyone. I'm not a big fan of primate research. If it can be avoided, which I think it can. So, what do you think can be the difference? The monkeys cannot, Of course, you can do much more with monkeys, no question. But at the point where we are, I really wonder. But is there primate research here at Scotland? Just out of interest.
Not yet, but we are connected with some primates as well, and there probably will be some projects.
Okay, so let's say if there's really a very compelling reason why something can only be done in primates, I think maybe a good example is the recent research on restoring, like you might have heard, like a brain-spine interface to bridge spinal cord lesions, and there the basic research has been done in primates, and I really don't see how this could have been done in humans, and it has a really very direct clinical application for many people who are now tetraplegic or paraplegic. So this would be an example where I think this makes a lot of sense, and in this sense I would say yes, primate research can enable research that is not possible in humans.
Yeah, and how it differs between human and people. So I think this question is about this brain-computer interface based on deep learning. And do you try different?
Yeah, we have. So there's definitely big differences between individuals. Probably we all likely have a fingerprint. We also have kind of our unique brain activity, which no one else has, and so there's definitely a lot of differences. And this is a really interesting topic for further research, yes. So is it possible that the questions are getting more, not less? No, this one we had, it's the first, or if it wasn't asked again. We had some more, yes. Okay, we had. Okay, how many data points in the training phase? So our window was, now I hope I don't give you the wrong number, but I think we had a 2-second time window at a sampling rate of 250 Hertz around that, so that would be around 500 data points per channel using, let's say, 40 channels. Depends on the exact study, but this is like a rough number that we would use. And
how many trials?
So I always, for the training, I always say 1,000 trials is a good number, but just because it sounds good, yeah. So there's nothing mentioned about 1,000. I would say it's just a number that if you really try, you can still get without subjects getting completely exhausted. So I always, for people now talking about movement paradigms, I always try to get around 1,000 trials, all classes combined. Yeah. And pre-training, very interesting point. We are just starting to look at that. There's a really interesting property of deep networks that often pre-training on different tasks helps for what you want to do. So in another project we are using deep networks for brain tumor segmentation out of images. And there we see if we use a network that has been pre-trained on ImageNet. And from what I showed you, of course, in this ImageNet competition, there are no brain tumors. There are cats and dogs and strange pieces of clothing. But still, pre-training a deep network on ImageNet helps them to find the exact borders of a brain tumor in imaging data, which is quite interesting. And so I think pre-training will be it's a very important topic to look at in more detail, but we haven't done this yet. Autoencoders, yes, would be exactly one way to even do unsupervised pre-training, right?
Is it possible to answer some questions later for you? For example,
Sure.
Okay. So it will probably take a few more, and then the rest will be answered by Professor Ball after
So-
the lecture. We'll probably record something on the video.
Okay.
What the best strategy for making significant contribution in AI?
Okay, so it's a multiple choice questions, A or B. Having knowledge on area like neuroscience deeply and work in a team of experts, or be like multidisciplinary specialist. Okay, this is easy, it's A. So it's definitely teamwork. It's the age of teamwork, but although I would say even in a team it makes sense to be not completely narrow in your expertise, but because else maybe you cannot talk to your colleagues. But at least, this would be my opinion, I would really try to work in a team, because there are so many aspects of this topic and you just cannot be an expert in everything. This would be my general take, but maybe you can also, as a one-man show or one-woman show, so to speak, you can also achieve something. So maybe it's A and B. Maybe. So frequency tuned neurons, yeah, sure, in the auditory system, yes. Very good questions. The ones that we use so far don't. They are purely excitatory. And it's another of these really basic things about, I talked about spiking neural networks versus non-spiking, where you cannot think, so why are neurons spiking? It's the same for inhibitory neurons. And so this in many situations, if you have a purely excitatory network in the brain, because something else that we do not have here is real recurrency, maybe that there are recurrent neural networks, but in the brain, it's not only within the local networks, but also between networks, that you have a lot of recurrent connections, and if you would build something like this, purely based on excitatory silences or neurons, your activity typically would explode and you don't have like a stable regime. But we do not know yet, from at least for what I know, what I'm aware of, it's really not clear if the usage of inhibitory neurons has some fundamental computational advantage. This is, I think, not clear and a really interesting question.
With two last questions.
Okay. Yeah, thanks for this question. So this is actually, so there are some benchmarks that have been proposed, but so in my opinion, the data is kind of suboptimal, and we are currently exactly trying to do this. So we made a really big collection of data in my lab over the last years. So we really want to publish a collection of more than 100 data sets of high quality EEG data that we would hope could be a useful benchmark for the EEG BCI field. So yeah, this is something that we are working on actually right now.
The last question.
Well, so not really, it's not only the location, but it's really the combination of location and the signal changes that are happening. So therefore, it's more complex, and because it's more complex, methods like the ones that I talked about today to make sense and can be, it makes sense to use them on such signals, if I understand it correctly. Else the whole problem would be kind of trivial, and we could just use some simple linear methods, but it's more complex, so these non-linear methods, I think they make sense. Yeah.
So let's keep the rest of the questions for, we'll find a way to have answers from Professor Ball for this question. Let's think